Hey there, here's a video on section 3.5 part 1 regarding application problems for exponential models. And so here we're going to talk about exponential growth and decay. So these models look a little different than what we're used to. We're used to seeing this, right? Y equals A times B to the X. I forgot what B was, the base. If B is bigger than 1, that was growth. If B was less than 1, but of course greater than 0, that was decay. A little different here. Our base is going to be E, which we know is roughly 2.7. But we're changing things up a little bit. The exponent is not going to be a simple x, it's going to be kt. T being time, k just being some sort of constant. If your k is positive, then you're going to have growth. Actually, let's do that in red and green. K is positive, it's growing. But if your k is negative, you're decaying. And that kind of makes sense, right? Because let's just kind of ignore this typical model and kind of focus on when k is positive, then what do you have? You have A0 times E, some positive number. Well, E is 2.7 roughly, right? We already mentioned that. If you raise 2.7 to some positive number and keep growing it, then of course naturally it's going to get bigger, right? Because 2.7 is a base bigger than 1. If k is less than 0, if A0 times E to a negative number, now remember E is 2.7. So you raise 2.7 to a negative number, guess what? You're going to have a negative exponent. So that actually becomes 1 over 2.7. And then your exponent changes back to being positive. But as you increase t, your time, this right here is getting smaller and smaller and smaller because that's a base that's less than 1 but greater than 0. So that's why when k is greater than 0 for this particular model of an exponential function, you have growth. When k is less than 0, it's decay. So let's look at a word problem here. And this is kind of cool because we're using this to help predict the population. So we're developing predictive models. For those who see all my football scores on the board, I'm using actually modeling for that. Those are more linear models, not exponential, but nonetheless, it's something that's kind of neat to do to be able to predict how the future is going to look. You can do it for a lot of things. You can do it for population, sports, healthcare, finance, whatever floats your boat. So let's look at this one here. Find exponential growth model for data from 1970 to 2010. So 1970 was that population 203.3. So I'm going to call it A0. And in 2010, the population was 308.7. I'm going to call that A. And our model looks like this. A equals A0. And I'll even tell you what model to use, that A. I want to use this A equals A0 times EKT model. So 308.7 equals 203.3 times E raised to the K. And I'm going to plug in 40 here. The reason I'm going to plug in 40 is I'm going from 1970 to 2010. So clearly that's 40 years. So these numbers, A0 being 203.3, A being 308.7, are consistent with little t being 40 because that's what we see here in the data that that's given to us. Now you got to solve for k. So this is pretty similar to what we've done in other lessons. Just got to divide both sides by 203.3. So 308.7 divided by 203.3 equals E40k. So 308.7 divided by 203.3, 1.518 equals E40k. And that's with log base E, 1.518 equals 40k. So if I work that out, and by the way, log base E is ln, in case you're curious. So I got to use my log properties, of course, here. This is why these are application-based problems. If I take the natural log of that in the calculator and then divide by 40, so 0.418 equals 40k, k roughly equals 0.0104. So your model is going to be this. And because our initial population is 203.3, we're going to keep that in for A0. And those are case positive, so this will be growing smallly or slowly, but growing. So that's the model we get. Okay, that was all just part A, so that was quite a bit of work. Part B, which I'll have to tuck in over here, by which year will the U.S. population reach 335 million? So I'm going to plug in 335 for A. And notice how I kind of left off the 6 zeros for the million bit for the million part, because that just takes up too much space. If you chop off the million part for both left and right sides of the equation, you're fine. Okay, we have this. And now our job is to solve for t. So 335 divided by 203.3, you get 1.648. Again, I divide both sides by 203.3. I'm going to take the natural log of the left side and divide by 0.0104. So again, you take the natural log of 1.648. Allows you to isolate the exponent using the log property we talked about. Remember, log base dx equals y. Same thing as x equals b to the y. So b to the y, e to that junk, x, 1.648, you just transform it. And you should get about 48 years. So if you think about it, that's the year 2018, right now. Is the US population that high? Well, we could go to Google here, current population of the US, 323.1, or just as kind of an interesting website. It calculates the population. You can see the US population keeps growing. There's a lot of people being born. US population is growing a little more slowly. We don't have quite the birth rate. Of course, people die too, so that is a negative loss of people, or if that makes any sense. But anyway, so that's what we see there. So pretty cool. Now you could actually check your work using a feature in the calculator. I'll write out the steps, but it might be better to actually find me in person. It doesn't make too much sense. But you should locate a button called Stat, and then there's a sub-menu called Edit. And if you hit Enter, you'll see an L1 and L2. L1, you're going to type in these numbers here. L2, you're going to type in these numbers. And if you're unsure of how to clear, if you do have other numbers in place of them, all you have to do is just go up to L1, highlight it, and hit clear, and hit the down key. That clears it. Or go up to L2, hit clear, hit the down key. If you already have stuff under L1 and L2. These are going to be like X and Y values, basically. The calculator will store that. After you do that, you're going to hit Stat again. Then you're going to select Calc. And then you're going to select Exponent Reg, which basically creates an exponential regression model for you. After you do that, you're going to select Calculate. And you'll notice that we'll say X list is L1 and Y list is L2. And then it'll just generate the model for you. Now you will get something that kind of looks like this. They'll say B is like 1.014. And they'll use the model as like A times B to the X. So a little different than what we're using with E to the X. But all you need to do is subtract the B value by 1. And that should be our K value, which is 0.014. And that's what we got. So this way you can kind of check your work. But do find me if you need a little more work or support with this. Okay, and when we're doing group work in our next class meeting, we'll make sure you guys practice the skill. Okay, the next one's talking about half-life. As the name implies, it's basically the time for a substance to lose half its amount. And hence you get the name half-life. So strontium-90 is a radioactive substance. That's not good. It has a half-life of 28 years. So what it means is that it takes 28 years to lose half its original amount, because we are decaying. That's loss. So we're going to start with this formula again. And I would tell you that, hey, let's use this formula. And I'll tell you what these things are. Now, we're not told A and A0. But we know how they're related. And that's important, because we're going to use a little bit of critical thinking here. Critical thinking, kind of big deal. We've been talking about this, and you guys hear this term used often. Well, now you're gonna actually see critical thinking in practice, because how do we think critically here? I didn't tell you that what A and A0 were, but I told you that they're related with the half-life. The time for a substance lives half its amount. So A would have to equal half of A0, half the original amount. That makes sense, because that's what half-life is. But when T equals 28, because you're told that in the problem. So this relationship holds true when T equals 28. Let's substitute that into our equation here. Replace A with half of A0. So if you have a hard time seeing that, still find me. I'll help you make that clear. But recognize that we want this to be half of this. That's why I have that relationship when T is 28. Oh, and I should put T, a little t is 28. It's my bad. So what happens is the A0s cancel from each side because we're just doing multiplication. So 1/2 equals E28K. Well, I'm going to take natural log of both sides. That allows me to isolate the exponent, just like we've done in the previous problem. And if you solve for K, I think you get negative 0.025. Use a calculator to do that. So your model is this. A equals A0 times E negative 0.025, where K is negative, so this is decay, times T. We don't know what A0 could be for this particular situation, because it really could be anything you're starting with. And you could use the procedure we had in the calculator that I showed over here, stat. What you would do is you would replace this with 28, and you want to make sure that these are off by a factor of 2. Like I made up 100, that's made up. Because if you start with 100 grams and it goes down to 50 grams, that's falling the half-life of 28 years. And you'll probably get a B value that I think is 0.975. So if you do that minus 1, you will get negative 0.025. So that's the way you can check your work. Now part B is asking us how long does it take for the substance to go from 60 grams to 10 grams. So I'll need to create a new sheet here. 10 grams, 60, E, negative 0.025 T. So you're going to do this in a very similar fashion as we did in the previous example. You're going to solve for T by taking natural log of 1/6. And I'll do that in my calculator right now. Natural log of 1/6. Nope, I'm in the wrong place. Let's try this again. Natural log of 1/6 divided by negative 0.025. And you're going to see that T is roughly 71.67 years. So you can see that this is not a good thing. If you think about when the U.S. dropped the atom bomb in Hiroshima and Nagasaki to end World War II in 1945 when Truman was president, even then, 70 years afterwards, there's still quite a bit of radioactive remnants from that bomb. So, not a good thing. It's always kind of good to understand why radioactive decay can stay for a while. So, let's look at another model, logistic growth model. Logistic growth is a good model to consider because it's a little more realistic. What happens is that things will increase quickly, as you kind of see here, but then they slow down as time passes. There's a bit of a decreasing rate of growth. A good example would be looking at people infected with the flu. Let's say we use Sacred Heart, for example, and like 5 kids show up to school really sick. They get the kids sick in their class. Then those kids get more people sick and more people sick. And so it increases very quickly. But ultimately, it's going to slow down because by that time, everyone in the school is sick, and we only have so many people at the school. We don't have an infinite amount of people. So unlike an exponential model, which does this is an exponential model, logistic does this. It kind of levels off. That's the logistic model. And the way you keep things limiting is by having the model set up as a fraction and figuring out what C is. C is what we call the limiting factor for size. So it's basically the population of your area. That's why we have the 30,000 as a numerator, because we have 30,000 people in the town. Let's work these out. So for part A, you're asked to find how many people were infected with the flu when the epidemic began. Let's say this is for Menlo Park. Menlo Park's got about 30,000 people. You're just going to straight up just plug in 0 for T and figure out what you get. And if you do that and work it out, you should get about 1,429 people. So use your calculator and make sure you surround the denominator in parentheses. Otherwise, the calculator's going to follow order of operations, get you a different answer. So make sure you do 30,000 parentheses divide parentheses 1 plus 20 times E, negative 1.5 times 0, blah blah blah. Work it out. So about 1,429 people were infected right when the flu, right when we were during our study. 4 weeks later, so about a month from now, how many people are now infected? You can see this goes up by quite a bit. If you do that, I think at 28,523 or 853, I'm going to work it out myself here. 1 plus 20 times E, negative 1.5 times 4, and yeah, 583 people. Okay, that's a pretty big jump in 4 weeks. But of course, it's going to slow down a little bit because if I were to say what happens after 6 or 7 or 8 weeks, it won't increase as much as it did from A to B. The limiting size or factor is 30,000 people, that being your numerator. Also, let's think carefully. That approaches 0, that term in our formula, when T is approaching positive infinity, right? When T gets really, really big, what's happening is that you have E negative 1.5 times T. Remember, you have a negative exponent there. And you have E as your base, which is 2.7. So it makes it a decay model. So since that's approaching 0 as T gets really big, you're multiplying that to whatever A is, and these kind of just go away. So you got C over 1, and that's why your amount equals C as time gets really large. And hence we call it a limiting factor or size. Okay, last one. Let's talk about Newton's law of cooling. This is a very detailed formula. I don't expect you to memorize it. I'll give it to you. I'll even tell you what the things represent. T says the constant temperature of the surrounding medium. That's actually going to be room temperature. It's a very fancy word. Medium means like what you're passing through, the air around you, I guess, is surrounding. T0 is initial. T is your final. T0 is initial. T is final. And what we're doing here is we're looking how something cools down, right? So we're looking how something's cooling down as time passes. And then little t is time. And I'll give you the units here. So we want to see how things are cooling down. We're given some data here. The 210 will be your T0. That's your initial temperature. 70 is room temperature at C. 140 is your T final. It's the temperature we want to get this thing to. And it takes 30 minutes to cool it. That's little t. So we plug all this stuff into Newton's law of cooling. So 140 equals 70, which is C, plus 210. So the cake's really hot. You take it out of the oven, it's 210 degrees Fahrenheit, right? You put it at room temperature, which is 70 degrees. So it's going to start cooling. And it's modeled by this, function that we're working out here. We don't know what K is. And of course, it takes 30 minutes to get down 140 degrees Fahrenheit. So if I want to work this out, again, it's very similar to the way we've worked out all the other examples. You want to isolate the power. Divide by 140. Write it as a log. And use your calculator. Trust it. It will help you out. You should get negative 0.023. Hopefully that makes lots of sense. Yeah, negative 0.023. Your model is this. This will help us to solve for the temperature for any particular time for the cake we're baking. And this is using the data that was given to us. Hey, at 30 minutes, it cooled down this much. And it could vary on what you're actually baking, depending on the content of your baked items or goods. Brownies might cool differently than say a pie or a pizza or cookies or whatever. But remember, our room temperature is still 70, and it was 210 when it left the oven. So we're going to go with that. Now for parts B and C, what we need to do is get the temperature cake after 40 minutes. So you're going to let little t be 40. The t is going to equal 70 plus 140 times e negative 0.23 times 40. And for part C, you're asked to solve for how long it takes to get to 90 degrees Fahrenheit. Let's say 90 degrees Fahrenheit is the right temperature. The temperature where you can finally slice into the cake. It's not going to fall apart. You put frosting on, you can eat it, not burn the roof of your mouth. It's not good. So we need to solve for t in this case. Little t. And again, capital T is 90 here. So if we work it all out, you got 20 equals 40. Actually, you know what? I'm going to let you guys work it out. Pause the video, tell me what you get. Okay. Hopefully you got capital T is about 126 degrees Fahrenheit. Now if we got little t is roughly 85 minutes. If you do need help with that, just find me. I'll show you the calculation again. But it's very simple. We've just done already. So that's it. That concludes the video, and we'll check again soon.